Thank you, Kendra, and thank you, Ben, for help. And good morning, good afternoon, and good evening, everyone, depending upon where you have joined from. And welcome to my session, which is on SQL Server indexes back to the basics. So my name is Satya Ramesh, and I work as a senior consultant for SQL Maestros. I do present in Data Platform Day and webinars organized by Data Platform Weeks. And you can learn more about me on sqlmaestros.com on this link. And you can follow me on Twitter at satyaramesh230. So this is a quick introduction about me. I don't tell more about myself. And here is the agenda of our today's class. And today we are going to discuss the basics about what is an index and cluster index, non-cluster index. Remember, both are row store. We are not going to cover column store indexes here. And we'll just discuss a couple of points on what is a good candidate, which is a column that is a good candidate for a cluster index. And then we will go and discuss a couple of topics around covering index, what is covering index and how to create it and why do we need it, etc. And then a few basics around page splits, fragmentation, and fill factor. And please remember that this presentation does not cover the column store indexes and indexes on XML data types and spatial data type columns. So with this, let's quickly go ahead and discuss what is an index. So you just go and type what is an index online. You find lots and lots of definitions over internet, but to simply put it, indexes helps us in reaching to the data faster. That's it. So let's take an example of a textbook. Textbook has an index in the front and index in the back also. So for example, for the understanding purpose, just take a textbook first, beginning of the textbook, index in the beginning of the textbook. So we have all the chapters listed and page numbers next to each other. So let's say you want to visit chapter number 5 and you just directly open the index and see the index. Okay, chapter number 5 is starting at page number 200. Flip through the pages randomly and reach page number 200. Otherwise, you need to flip every page till the time you reach chapter number 5. So indexes are helping us in searching the data page faster. So if you're reaching to the data faster, then you're improving the overall performance. So that because you're cutting down the search performance. So to put it in simple terms, indexes helps us in reaching to the data faster. Let's assume this one. If you reach to the data faster and you find out the actual page, then it is your job to read that particular page. That means there comes IO, CPU, everything. But indexes are helping us only to reach to the data faster. Once you reach to the data faster, how fast your reading is depends upon individual, like the way it depends upon in computer terminology, IO subsystem and CPU processors, etc. So just to put it again, indexes helps us in reaching to the data faster. And to generally put it, we generally have two types of indexes. One is clustered index, other one is non-clustered index. We all know that we can have only one clustered index per table and we can have multiple non-clustered indexes. So starting from SQL Server 2008 R2, if I'm right, we can have 999 indexes on a table. So who will create 999 indexes, right? But still we have that limit. A table can have 1024 columns and 999 non-clustered indexes. So remember, just because we can able to create 999 non-clustered indexes, we should not create that many indexes. Again, that will hurt performance. And please excuse me if my voice breaks. I'm suffering with a little bit of cough and cold. Please excuse me on that. So we have two types of indexes, clustered index and non-clustered index. And a quick point I wanted to make is that a table without clustered index is called as heap. A table without clustered index is called as heap. So again, do not confuse a table. Even though the table has a non-clustered index, it is still a heap if the table do not have a clustered index. So that's why I'm just pressing on that particular point. A table without clustered index is a heap. So what is this heap, clustered index, etc.? So you just type this statement called create table, table name and couple of columns. Then you have a table and you can start inserting the data. That is your main table. Right now it is a heap. Heap means doesn't have any clustered index. That means unordered data. Now, for some reason, you want to arrange the data based upon any of the column. Let's say employee table, you want to arrange all the employees based upon their employee ID. Now you need some arrangement. You need to sort data based upon any of the one column. So in this particular point, you may consider to create an index. So now, just because you can create index, you have two options. One is clustered index, other one is non-clustered index. Let's say ID is a unique column. Generally, obviously, unique column, each employee will have their own unique ID. So that will be unique. So we generally consider to go ahead and create clustered index on top of employee ID column. So once you create clustered index, that becomes your table. So there is no more heap. There is no more unordered data. Once you create clustered index, the clustered index is your table. The clustered index is the main table of yours. Then after some time, whenever you create clustered index, SQL Server internally creates some structures. I'll talk about all those structures a little later. So that is quickly about clustered index and heap. So what is the use of non-clustered index? So whenever you create clustered index, the data is arranged based upon that particular column. In our previous example, employee ID. So all your searches, for example, select star from employee table where ID is equal to 10. So SQL Server will able to seek on that particular record. Now this particular terminology seek comes into the picture. So I just take a moment to explain what is seek and table, seek and scan. So in our previous example where we are discussing a textbook, to identify chapter number 5, if you just flipping through all the pages, then that is called scanning through entire textbook. If instead of that, if you just go to the index and identify the page number 200 and you quickly jump through page number 200, this is called seek. So scan means going through every data page. Seek means directly jumping through that particular page with the help of indexing structure. So that is the quick difference between scan and seek. So we have cluster index. We have we are searching on select star from table name where employee ID is equal to 10, and we have an index, so we are able to seek on that particular index. Now that we want to search on employee name do not have any index, so we do not have any index on employee name column. So if you search on name column, SQL Server do not have any navigation procedure to directly jump to that particular name that you are searching for. So SQL Server has to scan through entire clustered table. So if you want to improve the performance of that query, which is searching on name, then you may need to consider creating a non-cluster index on name column. So this is the quick difference between, this is the quick idea about what is index, what is cluster index, and what is non-cluster index, and what is a heap. So with this, we'll quickly jump into B-tree structures of both clustered index and non-cluster index. Just an example, assume that we are creating indexes on any character column. Let's assume a name column. Just for the understanding purpose, just assume we are creating index on our name column. So if at all you have created a clustered index on a name column, the data will be rearranged in B-tree format. B-tree means balanced tree. So create cluster index, index name. Let's say column 1 here, that is a character data type. Let's assume that, and we are creating a cluster index on top of that. So once you create a cluster index, a B-tree structure will get formed. If you observe, it is an inverted tree format. When I say inverted tree, because root is on top, leaves are at bottom. That is why we are calling it as inverted tree. So what happens? All your data will get arranged based upon name column. I mean, for example, employee name. All the data will get arranged based upon employee name. So let's say in the first page, if you see on the left-hand bottom side, A to F, all the names that are in between A to F will be in that particular page. Then G to M are in the next page, N to S are in the next page, and T to Z are in the next page. Once our entire data is stored in all leaf level pages, then SQL Server will start building an intermediate level page. So that means here, if you see our indexing structure in the intermediate level node, A to M. So all the data belongs to A to M is in that particular page, and N to Z is in the other page. Similarly, we have one single page on top, which is called root node. everything is, all the pointers are available there. So let's assume that you are searching for select star from table name where employee name is equal to Ben. So SQL Server will come to the root page, and it finds starting with B, and go to the root page. And if you want all the names starting with B, you need to go to this particular page where A to M is available. And from there, further navigate down to the leaf level page, and you will be able to find out Ben in the first page. So this is how SQL Server will navigate from top to bottom to identify the actual record. So non-cluster indexes is also similar to cluster index structure. Only thing is, cluster index is the table. That means even though you have created index only on one column, in the leaf level page, we have data of all the columns in our table. So let's say our table have 10 columns. You have created cluster index on column 1. So the data is arranged based upon column 1, but all 10 columns data will be available in leaf level pages. And if you come to the non-cluster index, if you create a non-cluster index on column 2, only the data about column 2 is available in leaf level pages. Other column data will not be available. So that is the main difference between cluster index and non-cluster index. I repeat, cluster index is the table. Even though you create cluster index only on one column, all other columns data is also available in leaf level pages. If you go to non-cluster index, in the leaf level page, you have data about only that particular column on which you have created an index. And there is slight, what you call a characteristic here. If that particular table already contains a clustered index, then that clustered key will also get included in the leaf level page. That is the one characteristics you need to remember. So that is the quick difference between clustered index and non-clustered index structures. Both are B-tree structures, both will get saved almost in the same way. Only difference is cluster index is the table, so all the data is available in the leaf level page. Non-cluster index is a copy of your table, so only the data on the column on which you create an index will be available there. So if you observe the intermediate node pages, intermediate level pages will have data about only that column on which you have created an index. Intermediate level nodes will have only the data on which data of the column on which you have created an index. Similarly, in the root level page also, you have the column data on which you have created an index. So this is the quick difference between clustered and non-clustered indexes B-tree structure. So just that you can able to create only one clustered index per table, because clustered index is the table, and whenever you create a cluster index, data will get arranged based upon that particular column, so that we can create only one clustered index per table. So just because we can able to create only one, we have to be very, very careful in choosing that particular column. That is why there are a couple of guidelines. There can be so many, but this is what generally experienced people follows, and a lot of best practices and guidelines will suggest. So the column should be narrow. What is the reason behind this? So when the column is narrow, I mean, we know this concept of column is wide and narrow, right? So the data is like if it is 200 byte character data type. So if it is a very big one, that is not a good candidate for a cluster index. So what is the good candidate for a cluster index? Let's say a fixed length data type, for example, an identity column on an integer data type. Okay, so integer is a fixed length data type, and on top of that we have an identity property. So if you have an identity property, the data will be ever increased, and there is a fixed length. And just because integer is a fixed length, the column is always fixed, meaning it is 4 bytes in nature. So these kind of characteristics you have to look on a particular column. Otherwise, what will happen if you go back to B-tree structure, as we discussed in the intermediate level nodes, we have SQL Server will store data of the column on which we created an index. Let's assume you have created a cluster index on a character length data type, which is of 200 length. So each record that you insert will occupy 200 bytes. So then imagine how many number of intermediate level pages you may need to fit entire data, and the level of index will increase. Let's say if it is a root is level 0 and intermediate level is 1, then 2, then 3. So if you have a wide range column, then number of intermediate levels will go more. So these are the things that you keep in mind. These are the things that you should keep in mind whenever you are deciding a clustered key. So these are the quick points. The good candidate is an integer data type, and if at all you have an identity property defined on that particular column, then it is even more good. The data should be ever increasing, like the way we have in identity property, 1, 2, 3, 4, like that, the data will get increased. So in one more example today, we will discuss why GITs are not a good candidate. So GITs are a good candidate, but not always a good candidate for a clustered index. There are scenarios, but today we will discuss downsides of a GIT if you choose that as a clustered key. So I hope selecting a good candidate for a cluster index is well and clear. The column should be narrow, and if at all it is a fixed length data type, that is good. And fixed length data type and should be narrow also. So both should be combined together. It's not that character 2000 is a fixed length data type, obviously, but it is not narrow. It is very wide. So we should find this combination. So it should be narrow in nature. It should be a fixed length data type, and the data that is going inside to the table should be ever increasing in nature, so that last page contention. So there are so many things. Page contentions we can avoid, and last page contention. I mean, page contentions we can avoid, and page splits also we can avoid, etc. So these are the quick best practices that you can follow while selecting a cluster index guideline. So with this, I'll quickly go into demos and I show you a couple of things. What all we have discussed just now, we will quickly go ahead and discuss them. So let me share my virtual machine. I hope VM is visible.
Yes, it's visible.
Yeah, VM is visible and fonts, everything is well and good. So let's start with the demo. So let's start with these basics. So let's go ahead and create a dummy database for our demo purpose. I'm naming it that dummy database as SQL Maestros _prod. I've just dropped the existing database and recreated that. And let us create a schema as well, just for the demo purpose, nothing else. And let me create a table with 4 columns. I'll come back and explain that. And let me insert this particular records. So let me execute it. And while it is executing, I'll go ahead and explain. So I'm just inserting 10,000 records into the table. If you look into the loop, let me come back to my table once again. So this is the table that we have created. This is the table that we have created with 4 columns. Column 1 is integer data type. Column 2 is varchar data type of 8,000 length. And column 3 is character of 10. And column 4 is integer data type. So now we are inserting the data into that particular table. So what we are inserting, this is the insert statement that we are doing. So into the first column, we are inserting the count. So where do we declare the variable count? So we have declared the variable here. So count is equal to 1. And while this loop is running, we are incrementing the count. So the values in the column 1 will be 1, 2, 3, 4 till the time we reach 10,000. And what are the data that we are inserting in second column? From the variable data 1. So where do we declare data 1? Here we have declared the data 1 variable. What is the data that we are assigning? So we are just replicating this particular word big data 1,000 times. So big data has 7 characters and we are repeating that one 7,000 times, and 7,000 bytes will get occupied. And just because it is a varchar data type, there will be 2 bytes overhead. So this particular value will occupy 7,000 bytes, 7,002 to be precise. And then we are inserting default A's. And then into the fourth column, we are inserting the data from data2 variable. So that is the variable that we have declared here, which is a random number multiplied by this constant value, and we are rounding that particular value. So idea is very simple. we are just inserting some random data into it. But the thing that you need to observe is that column 1 will occupy 4 bytes, column 2 will occupy 7,000 bytes, column 3 will occupy 10 bytes, and column 4 will again occupy 4 bytes. That means in single page, we will be able to insert only one record. That is the point I want to make here. So we all know that smallest storage unit inside SQL Server is a page that is of 8 KB. So with this kind of a data insertion, we are occupying one page per insert. That is the point I want to make by explaining all these things. So let's quickly have a glance at our data. So this is the kind of data we have, just a dummy data. Don't worry, we are understanding the indexing basics, not concentrating on exact values. So don't worry about the data. So now I have done a couple of tests before. So just to make sure everything is going good, I just cleared them. But please remember, do not execute these commands in your production environment. Okay. So I am enabling the statistics IO on. And let's execute our first query. So we are just doing select start from table name where column 1 is equal to 125. So we are just getting all the records from our table where column 1 matches any particular value. So before doing that, let me also enable execution plan and let us execute this particular query. So I have executed the query. Let us go ahead and look into the messages window to get only one record. If you see, in our results pane, we have only one record. To get only one record, there are 10,000 logical reads. So we have inserted 10,000 records, and each page will have only one record, so that we have 10,000 pages. To get one record, SQL Server has to scan through 10,000 pages. That is where it is taking time. If you look into our execution plan, it is showing table scan here. So SQL Server is scanning entire table to get our one record. So we want to improve the performance of this particular query. So column 1 is an integer data type, even though there is no identity property, but the nature of the insert is that always the value is always increasing. So column 1 is a good candidate for a clustered index because we have already discussed the good characteristics for a good candidate. So column 1 is a good candidate. Let's go ahead and create a clustered index on column 1. So I've just created a cluster index on column 1. So our table will be scanned and data will get inserted into our cluster table. And now our cluster table will become our main table. So please remember, our cluster table is the main table. So we don't have any other tables right now. That is our main table. So once we created the cluster index, let's go ahead and execute this particular system store procedure. This is a system store procedure. If you pass a table name, it will give us all the indexes that are present in that particular table. So if I execute sp_help index and I pass the table name, it will give us all the indexes on top of that particular table. So right now we have only cluster index, and cluster index is located on primary, and our cluster index is on column 1. So this is the index name. So this is the store procedure that helps us give the information about all the indexes on a particular table. So we have already created an index. Let's go ahead and execute the same query again, and let's observe the execution plan and number of logical reads that are happening. So I have executed it. Again, we have got one record. Let's go to messages window. This time, if you observe, there are only 6 logical reads. Earlier we have 10,000 logical reads. Now we have only 6 logical reads. So SQL Server has gone to has created a B-tree structure, and to identify column is equal to 125, SQL Server has gone to the root level page, navigate down from root to intermediate level, and intermediate level to respective leaf level, and finally identified our record. So to get that, we just need only 6 logical reads. So if you look into the execution plan, SQL Server is doing a clustered index seek. So whenever we have created a cluster index, we have a table that is our cluster table. Cluster index is the table. So we are seeking on clustered index. So this is where our queries are improving. So earlier, to get the same one record, we were doing 10,000 reads. Now we are doing only 6 reads. So this is where our indexes helps us in improving the read performance. So now Column 1 is fine. What if someone search on some other column which do not have any index? So let's say someone is searching on column 4 for some random value. The idea is very simple. It is not necessary that we should have an index on that particular columns, but if our queries can able to improve their performance, if there is an index, then we should consider creating one. So that is the case that we are going to discuss right away. So let's execute this particular query where we are searching on column 4, which we do not have any index. Let's execute this one. So I've executed this one. There is no data. Don't worry about the data. Let's go ahead and look into messages tab. So even though there is no records, there are so many logical reads. If you observe, there are 10,024 logical reads. So what is happening? Why do we need to read that many pages? So what is the execution plan right now? So even though there are no records, to search, sorry, even though there are no records, just to make sure that there is no record, SQL Server has to go through our indexing structure and identify and search for that particular record. So whenever we say select star from table name where column 4 equal to something, we have only our clustered copy. SQL Server has gone into our clustered copy, searched all the pages of our clustered index, but it couldn't find that particular record. So why is this happening? Why do we need to scan entire table? Because we do not have anything that says details about column 4. We have one clustered index on column 1. Data is arranged based upon column 1, so that our cluster index root level page has information about column 1. It doesn't have information about column 4. So just because it doesn't have information about column 4, it has to go through the leaf level page and scan everything. That is why more number of scans are happening. In this particular case, having a non-cluster index on column 4 may be helpful. So again, I'm just discussing in the perspective of basics. So whenever you are creating a real-time indexes, you may need to consider a lot of things. But as we are just going ahead and discussing basics, so I'm going through a particular flow, create an cluster index and non-cluster index and covering index. So let's go ahead and create a non-clustered index on column 4. So this is the syntax to create non-cluster index on column 4. So let's go ahead and create a non-cluster index. So all of us know that, right? So it is always good to create a non-cluster index after creating a cluster index. Right now we already have a cluster index. We are creating a non-cluster index now. So please remember that all non-clustered indexes by default includes clustered key in their leaf level. We have already discussed this point. So because of this reason, it is always recommended that create clustered index first and then create non-clustered indexes. Otherwise, what will happen? You can create non-clustered index first. You can create that, but what will happen later point in time? If you decide to create clustered index on any column, then all your non-clustered indexes have to be modified to include this clustered key. So that's why it is always better to create a cluster index first and then create a non-cluster indexes. So in our sequence also, we have already created a cluster index and now we are creating a non-clustered index. So let me go ahead and create a non-cluster index. We have already created. And if I execute this particular query, and if I go to messages window, we are doing very, very less logical reads here, only 2 logical reads. And if I go to the execution plan, we have a different execution plan right now. It is a seek and lookup plan. So where we are seeking on our non-clustered index. If I zoom in, sorry. If I zoom in, we are seeking on our non-clustered index. So we are seeking, and while we are seeking, what are the columns that we are getting in the output? We are getting column 4. Column 4 we are getting because that is the column on which we have created a non-clustered index. And as we already discussed, on non-clustered indexes by default include clustered key, so that column 1 data is also available in our non-clustered index. So by doing index seek, we are able to fetch column 4 data and column 1 data. And now why we are doing this key lookup? Because our query is asking for select star. So we have 4 columns, column 1, column 2, column 3, and column 4. In our index, non-cluster index seek, we have data of column 4 and column 1. To get column 2 and column 3, we need to go and look into our clustered index. So that is why key lookup is happening. So if I zoom in, and if you see, if you look into the object, this is our cluster index object. So we are looking into cluster index to get what columns? To get column 2 and column 3. So index seeking on non-cluster index to get column 1 and column 4, and then look up into cluster index to get other 2 columns, which are column 2 and column 3, then join these 2 data sets together using nested loop join, and finally process the output. That is what happening here. So this is fine. That is how SQL Server behaves whenever there is certain kind of a need exists. But what happens is that if at all SQL Server has to do a lot of these key lookups, let's say if I just change this particular operator from is equal to operator to greater than operator, and if I execute this particular query again, and if I go and look into the execution plan, if I have hover over, now SQL Server is doing a clustered index scan. Earlier, what has happened? We just changed equal to operator to greater than operator. And earlier we were having seek and lookup plan. Now we are having clustered index scan plan. What is happening? So this is called tipping point behavior inside SQL Server. There is no hard limit to that, but somewhere around 25% to 30% pages, if SQL Server has to touch to get the output, then SQL Server may consider to scan entire table instead of doing the seek and lookup plans. So that is what happened. When I just changed the equality operator to greater than operator, then there are a lot many pages SQL Server has to touch. So SQL Server has just decided that instead of doing seek and lookup, just go and do an entire cluster index scan. Is it good? Is it bad? We cannot decide, but we can definitely help SQL Server to take better decisions. In this particular case, if at all SQL Server is doing cluster index scan just over a tipping point, let's say if the tipping point is 30% of data pages, if it is 31%, then we may use covering index to avoid that cluster index scan. So what is covering index and why covering index helps SQL Server? So here, if you see in our earlier example, if I change this is greater than to is equal to again, and if I execute this one, and if I go and look into the execution plan, it is seek and lookup plan, meaning we have 2 columns in seek and we have 2 columns in clustered index. So to get these other 2 columns, we are looking into cluster table. What if the other 2 columns are also there in our non-cluster index? Then there is no need for SQL Server to go and look into cluster index, correct? So that is where include keyword comes into the picture. So if I scroll down and drop my existing non-clustered index and recreate our non-clustered index, this time by including column 2 and column 3. So if I execute this particular query, SQL Server will create a non-clustered index on column 4, and we already have a cluster index on column 1, so that in leaf level pages, we have data about column 4 and column 1. Now that we have included column 2 and column 3 also, so that our non-cluster index has all 4 columns data. So if at all, if you go ahead and execute this particular query now, instead of doing a cluster index scan, SQL Server will simply do a index seek on non-clustered index. You can all see this one right away. So right now index seek is happening on a non-clustered index. So to avoid that cluster index scans, this is a kind of a workaround. And why this is called as a covering index is that this particular index is covering all the columns that this particular query is needed. This particular query needs column 1, 2, 3, 4, and this particular index is able to serve all those columns. That is why this particular index is called as covering index. Remember that whenever you put the columns in include keyword, these 2 columns are not available in intermediate level and root level. That means if your queries are searching on column 2 and column 3, then again SQL Server has to go to clustered index, because there is no way other than that for SQL Server to find out that particular records. So with this, I hope all the concepts of cluster index, non-cluster index, and good candidate for cluster index and covering index are clear. Let me quickly go and discuss quickly about index fragmentation, and then we'll come back and discuss a quick demo, and we can close today's class. So to do this index fragmentation thing, I'll quickly take MS Paint. I hope you all can see the MS Paint window. And
we can see it. And Ramesh, you're good in time, so don't hurry. You've got time.
Yeah, thank you, Ben. Yeah, so let me draw a B-tree structure quickly. Assume that we have these leaf level in data pages here, and we have a couple of intermediate level pages, and we have a root level page. And we all know every page knows what is its next page and what is its previous page. Every page knows what is this next page and what is its previous page. Every page knows what is its next page, and every page knows what is its previous page. These are all done by W linked list inside SQL Server, so that whenever there is a ordered scan, SQL Server can able to use this W linked list to do that ordered scan. If it is descending order, it's backward scan. It is ascending order, it is a forward scan. So all these linked list will help us in SQL Server in scanning, in sequential scans. So let's assume we have this kind of a B-tree structure, and assume that this kind of a B-tree structure was created only if you create an index on a name column. You have created an index on name column, and this B-tree structure got created. Okay. And now assume that all the names starting with A, all the names starting with A are in this particular page. All the names starting with B are in this particular page. Just for example's sake, all the names starting with C are in this page. All the names starting with D are in this particular page. Let's call this one as page 2, page 1, page 2, page 3, and page 4, and so on. So now a new insert comes in. Our index is tightly packed. We have inserted data, we have created index, everything is fine. And all the names that are starting with A are in page 1, all the names starting with B are in page 2, everything is tightly packed. Now that a new insert comes in, starting with name A. So to maintain the logical order, what is the logical order? So in logical order here in name column is that alphabetical order. So all the names starting with A should come first, then B, then C, then D. So this is the logical order. Whenever we have something called logical, then we will have physical also. What is the physical order? All the data that ends of here, if you see, all the data that start with A are in page number 1. Immediately the next continuation page is page number 2 that has all the data starting with B. So then C, then D. So the data pages are also next to each other, and that is called physical order. So we have logical order and we have a physical order. Whenever a new insert comes into the picture, if the new insert is starting with page, starting with A, name that is starting with A, that new record has to go into this particular page. And there is no empty space in this particular page. But to maintain logical order, the new record has to go and sit in the same page. In this particular case, what SQL Server will do is that SQL Server will create a new page at the end of the file. A new page at the end of the file. Let's call it as page number 5. And move most of the times 50% of the data, but not always. Move 50% of the data from page number 1 to page number 5. Once we move the data from page number 1 to page number 5, then all the linked list has to be modified. So what are the linked list here? So for page number 1, the next page is not this anymore. The next page is page number 5. And what is the previous page for page number 5? Previous page for page number 5 is page 1. And what is the next page for page number 5? That is page number 2. All these kind of a linked list has to be modified. So once these linked lists are modified, then everything has to be logged into the log file. Unfortunately, this is fully logged. there is no minimal logging, etc. Entire this linked list modification process is fully logged whenever the page split happens. So the page split happened, the data from page number 1 has to be moved into page number 5, and all the linked list has to be modified and logged into the log file. And finally, the new insert will go and sit either in page 1 or page 5 according to our logical order. Similarly, if any other new record comes into the picture that is starting with B, page 2 has to split, then page 3 has to split, then page 4 has to split. Over a period of time, all these page splits causes the data to spread across the disk, causing mismatch in physical order. Physical order is not maintained. Logical order will be maintained by the mechanism of linked list, but physical order is not maintained. That is because of page splits. This phenomena is called as fragmentation in SQL Server. So that is called fragmentation in SQL Server. How do we identify how much an index is fragmented? We have this particular DMV available inside SQL Server, sysdm-db index physical stats. This is a DMF, sorry, which accepts 5 input parameters. We will see that in an example now. And if that the output of that particular DMF has one column called average fragmentation percentage, if that particular percentage is less than 5, we can ignore that particular fragmentation. If the fragmentation percentage is anywhere greater than 5% and less than 30%, then we may consider to reorganize the index. And if it is greater than 30%, then we may consider to rebuild that particular index. Let's go ahead and quickly discuss the example of index fragmentation. I hope all of you can see the VM again, and we are in index fragmentation demo. If you face any difficulties, let us know in the chat windows. So I am just choosing TempDB for this particular demo. I'm creating a table called T1, and that has 2 columns. First one is unique identifier, and I'm inserting the data into that particular column by using a default constraint by using new ID function. So consider this is a GID column. So new ID function will generate a random value. So new ID function generates random value. There is no guarantee that the value generated now is greater than the previous value. So there is no guarantee, just a random value. And we have another column called character 2000. We are just inserting some default values there also. So if you observe our columns and the index structure, table structure, in single page, we can able to fit only 4 records. If you see character of 2000 and unique identifier, if you observe that, we can able to fit only 4 records into a single data page of SQL Server. Let me create this particular table. The table is created, and if you observe, we have created an clustered index on column 1, which is a GID column. That is a random value generation column. So now I'll quickly generate this loop. So please consider stopping this loop within 2-3 seconds. Otherwise, your machine will hang because this is going to insert a lot of values. So I'm just inserting this one, and I quickly stop it. So I've just executed the query for 2 minutes. So this must have inserted some records into our table. And as we already know, column 1, we are inserting a random values, and we have a clustered index on column 1. So to maintain the logical order, SQL Server may have done page splits. Okay. So, and that must have caused some fragmentation. So let's go ahead and see how much our index is fragmented by looking into this particular DMV. So sysdm index physical stats is DMV, which will accept 5 input parameters, database name, object name, and we are looking into cluster index. And we have a couple of other parameters also, that is partition and other one. So you can explore more about this particular DMF later. So let me execute this particular query and look into the actual fragmentation percentage. So look at that. Our index is fragmented 99%. So what has happened? I have randomly inserted values by using this while loop, and this while loop must have inserted some records, and just because our only single page can hold only 4 records, in the first insert 4 records must have gone into page 1, and then later 5th record must have generated, that has to go into the same page. There is no space, page has to split, and that is happening continuously over a period of time. And so many page splits have caused fragmentation. So right now the fragmentation is 99%. So earlier we have discussed guidelines. If the fragmentation is greater than 30%, we will just go ahead and do rebuild. So this is the statement for rebuild. This is the statement for reorganize. We will just put alter index name on table name, and we will just put this keyword called reorganize or rebuild. So right now our index fragmentation is greater than 90%. So I'm doing a rebuild. I've just done index rebuild. Once we done the index rebuild, let's go ahead and check the fragmentation percentage again. So if you see, it is 0.04. It's almost 0. So our index is not fragmented. If I run the loop again, then again so many inserts will happen that will create fragmentation again. Then we need to rebuild or reorganize again. So with this, what we must have understood, this is a continuous process. That is why we need to do index maintenance, and that should be done in off-peak business hours. And now, why in the first place these page splits are happening? Page splits are happening because for a new insert that is coming, there is no place to go and sit in our existing pages. What if there is some space for the new record to come into and sit there? So if at all there is some empty space in the existing data page, then new record come and sit there. There is no space, so that's why page split is happening. So that gives us idea that what if there is some empty space? How can we create that empty space? So fill factor is the option that we should consider to tell SQL Server that while creating an index or while rebuilding an index, how much empty space it should leave while creating or rebuilding index. So let me drop our existing index once. And if you see our query, I'm creating an index on column 1. And while doing that, we are telling SQL Server that fill factor is equal to 50. Why we are telling fill factor is equal to 50? What happening is that we are telling SQL Server leave 50%, fill only 50% of the data. That means other 50 will be left. If I say fill factor is equal to 90, that means I'm telling SQL Server that fill 90% of data page, leave 10% empty. So don't get confused. Don't think otherwise. Fill factor means how much space you want SQL Server to fill in your data page. In this particular example, I selected 50, but this is not the right approach, but I'm telling you why. We need to start somewhere at 90, and then we need to observe the page splits per second. And if it is happening too frequently, then we need to reduce that to 85. Then we need to observe page splits again, then come down to 80, like that. But anything below 80 is very, very difficult, because in this particular example, I had put 50. That means what? I'm leaving 50% empty space in all my data pages, That means what? Whenever I read, so what happens earlier to store 10,000 records, if I need 10,000 pages, now to store same 10,000 records, I need 20,000 pages. If someone do select start from table name, earlier I am reading only 10,000 pages. Now there will be 20,000 pages to read. So there will be more IO involved, there will be more CPU involved, and you all know that 8 KB page will be latched into the buffer, so that you're occupying 8K page, and that has 50% empty. So you need more memory also. So there are a lot of implications if you go a way down of fill factor, but if you want to avoid page splits for certain point of time, then you can able to consider fill factor values. And pad index is equal to on. This tells SQL Server that use the same value in the index intermediate level pages of our index also. Fill factor is for leaf level pages, pad index equal to on, then same fill factor is applicable for intermediate level pages of our index also. So if I create this particular index with fill factor is equal to 50, then if I execute this while loop again, and if I stop it, and let's go ahead and see the fragmentation. It is 72% now. So earlier it was 99% with that 2 minutes execution. Now it is 72% only. So what is happening? Earlier our page can fit only 4 records. if I put 90%, new record anyway cannot go. That's why I'd put 50. So you need to figure out optimal value for your machines by testing again and again. And once we change the value, you need to monitor page splits per second and how frequently your indexes are fragmenting, and then change the value, bring the value down. But remember, if you bring the value too much down, you need to have more number of, you need to do more number of IOs, and you need more memory as well. So I hope all these concepts are clear. I think, Ben, we are on time. I think I have covered almost everything.
Yes. We have a few questions, so we're absolutely perfectly on time to show you a summary and then get to those questions.
Yes, thank you, Ben. Thank you everyone for attending the session. So here is the quick summary of what we have discussed till now. So we have discussed what is an index, and we have discussed what is a clustered index and what is a non-clustered index. Both are row store, and we have discussed a couple of basic characteristics of a good candidate for a clustered index. And we have discussed about covering index also, how covering index helps us avoiding key lookups, and why do we need to create a covering index, etc. And then with the example of paint, we have discussed what is a page split and how does that cause fragmentation, and what is fill factor, and what are the advantages of fill factor, and what are the disadvantages of the fill factor if you bring down the fill factor value way below. So I think with this, I'm done with my session. I'll good to go with Q&A.
Kendra, do you want to ask the questions, or do you want me to?
You can go for it, Ben. That'd be really fun.
Maybe Ramesh, thank you very much. I think you did really well. First and most upvoted question is, will you share the slides in the demo code?
Yeah. Yep. Okay. Everyone, immediately after this session, I'll just email that to Ben.
That's good, and Ben will publish it then on the GitHub.
Yes, he will.
Great. Hello, Ben.
Let me just take that opportunity to quick. Thank you so much, Satya. Great session.
Thank you, Ben. And the next question?
You had a lot of feedback with great session and great demos. So, but the next question that one question you already answered during your presentation was how to choose the right fill factor. So you answered that already, and Martin also backed you up here and said that this would be the way that he would do it. The question would be, the next question would be, will I need tuning my index to avoid using key lookups? And when is heap better than table with a clustered index?
Yeah, so if you have a very small table, let's say less than 1,000 pages, and that time scanning will be better, I could say. And it's obvious to leave it for SQL Server to decide seek is better on scan is better. And sometimes if you can play around and try to create some permutations and combinations of columns and compare and test all these combinations. But most of the times heaps are better for, scans are better for a smaller tables, I could say. But if you have a very large table, then you should consider creating indexes on the columns on which you are searching.
Yep. And Uwe also commented on that he is writing a blog series about heaps and pros and cons of heaps. And the first 2 articles are already online, and the next will come soon.
Okay, good. Uwe is writing that.
Yeah. And then there was a question, another question. The question is how to check if all my pages are fragmented or only few. So what exactly does the fragmentation number tell you?
So overall, how much our index is fragmented. We won't get that which particular page is fragmented like that. We will get overall percentage that index is fragmented. That is what we get here.
Yeah. So do you know of a way to check only a few pages, or?
No.
So the DMVs always cover the entire table structure.
Yes, the entire table structure. So we have this DMF that will give us entire DMF, entire index time. Okay. So anyway, if you want to rebuild also, we will be able to rebuild the entire table right now. So even if you're able to find out, that doesn't help us.
Yeah. Then I think you've answered all the questions that were open.
Yeah.
It wouldn't let me put a question in the panel. Can I ask because since I'm a panelist, it actually just wouldn't let me add a question. Can I ask a question?
Please go ahead.
So my question is, so if folks who attend in this session, if they want to continue learning, how would you recommend, like, what are the next steps you would recommend people to do to build on what they learned here and to keep going if they're just getting started?
Yeah, so I just recommend people to go through the Microsoft documentation of indexing structures. So once we understand how the data is stored inside the database and inside storage engine, etc., then we will have better, we can able to take informed decisions. So I recommend people to go through Microsoft documentation in MSD and say on index architecture first. So once people read that, then they will be able to understand what is the difference between clustered, non-clustered, and column store per se. Sorry. Column store. So once they have the basic understanding by going through that documentation, then they can try out a few kind of permutations and combinations on their own.
Great. That's actually a really good point. The Microsoft documentation, we can start. It's like easy to take it for granted after working with it for a while, but it's really good and really carefully written to be human consumable.
Yeah. And it's available everywhere for everyone.
Yeah. Yeah, I agree. The documentation on the index is really good.
Yes.